So the lecture on randomness. So what is randomness, and what we're talking about in this lecture is about distribution of many uh, numbers. How I'm going to manage if I do one thing for so many iterations. How can I gather that data and put it in some manner that you can handle it better, right? So that is what we're going to look at. So yeah, so the few terms here that we have to consider. One is distribution. So what is distribution is? Well, obviously when you read this, I know you will get confused, right? So the best way that I can explain this is what is that what they're talking about in this graphs, the histogram, right? So if I explain this, I think it's better than I'm just trying to read the same thing that you can read here and just putting this in other words. So let's look at it like this. Let's say I have in the same way that they're talking about here 10,000 random floating point numbers uniformly distributed from 0 to 1. What does that mean, right? Okay, so let's think about this. Now I'm going to, if I throw a number, or if I have a number in my mind, I can write it down, like for example 7. So that is came to my mind, so I just write it down, and I'm thinking again I will get another number 10. I will stay and think about again another number 20. So these are actually genuine random numbers. Why? I don't process any equations in my mind, right? I just come up with some numbers. So that's called random generator. So that's why I said there's no such a thing exists in the world that you can actually do the random things like that. Whatever it is, not if you following a sequence, it's never going to be a random, right? But you can think of numbers without following a sequence. In that case, that is random, right? Well, so that is something that most of the people debate in the programming world. How are I really going to generate a random number? Well, you have opportunity if you want to try it, come up with something that doesn't follow any sequence, right? Why I'm saying that? So I explained that also in the last lecture. So if you're using a rand function, and if you run rand function in two machines, it will give you the same sequence, right? So it's not that good. Okay, anyway, back to lecture. So I can think of numbers like that, right? Even this one can give you 1 million also, right? That's a huge number. So that is also a random number, right? So like that, if I number this is the first one, second one, third one, fourth one, and so on. I'll do this 10,000 times. So this is the last number here is 10,000 times. So I did this, and then I get 1 for the last one, 10,000 times, right? Okay, so these is random generated numbers, and how can I distribute this into the range? So there's a range here. What is the range here? Well, 0 to, right, 0 to 1. Okay, that is your range. And also the numbers that I will have, so it says here 0 to 1000, right? So that is what is this means? Well, this means, well, these numbers I get here, right, can repeat itself. Like for example, I can have 10 here. Again, after a few other times, I can count 10 here. And again, after a few times, I get another number like, let's say the last one is 10 too. So if you count these numbers, 1, 2, 3, 4, and so on, well, how many times, how many occurrences you have this, right? How many occurrences you have this, you can say, okay, I got that 1,000 times, right? So like that, I can actually group it, right? Right. So in this case, instead of I'm just saying only one number, I just set it up some range, right? So let me explain this much better. So now you know the scenario. What I'm doing is I'm generating numbers 10,000 times, right? Let's see what can I do with it. How can I map this to 0 to 1? That is the first question, right? Right. Okay, so if you want to map it to 0 to 1, these are integer values actually, and I want to have it a floating point number. So what can I do is I can come up with the equation for this, right? So the equation for this is, let's say I'm taking a random number. So this is generating these numbers, right? And then let's limit it by modulus 100. So what does that mean? Well, that means each one of these numbers I'm going to divide by 100. And I get the remainder, right? So the remainder is the only thing I'm going to get. Divide by 100 and get the remainder, right? Divide by 100 and get the remainder. Right, so one question I would like to ask you. What is the remainder here? So what is the remainder means first? First think about that. So if I have 7 divided by 100, how many hundreds do we have for 7? Well, we don't have much, so it is 0, right? So what is the remaining value? Well, that is 7, right? So how do I generate this number back? Well, you multiply whatever the answer here by 100 and plus the remainder, right? For example, if I have 250, divided by 100 is what? I will have 2 of the hundreds and the remainder is 50. So I multiply this by 2 hundreds plus 50, right? So I get 200 plus 50 is equal to 250. So this is how you just generate things, and this is what this mod means. Mod means I'm taking out this value, right? Not the other. So I just ignore this part. I don't need this one. I'm just getting the remainder. So that's what the mod means, if you don't understand what this mod is, right? Okay, so now just taking the mod, so it is 7 will be there, and yeah, in this case 10 will be there. Whatever is less than 100 will be there as is. But if you come to here, well, this will be equal to 0 because 100 can divide this one perfectly. So there's no remainder, right? Like that. So you will, now you can see, even I have big numbers or small numbers. Now this one I will have some range. So what is this range actually? Well, this range is from 0 to 99. So I get that. So it is good now. But still, those are integers from 0 to 99, right? That's not what I want. I want 0 to 1. So in that case, what can I do? Well, the maximum number I can get is 1, right? So, in order to do that, actually, if you have 101 here, for example, then I get 0 to 100, right? Then I get 0 to 100 if I want that. So in that case, it will cover the 0 point here and then the 1 right here, if you have 101. Well, it's all up to you, whatever the range you get, right? So if it is 101, it's pretty good. If you can address the 1 here, and if you want to address the 0 here, yeah, 101 is a good idea. But anyway, so it will give you 0 to 100. So in this case, I don't want that. I want 100 to be 1, right? So in that case, I divide everything, the whole thing by 100. So in this case, whatever the value I get, I divide by 100. In that case, it will fall into this range, right? So the maximum number I get is by divide this whole thing by 100 is somewhere here, right? Okay, and yes, so I can do that. So if I get 0 here, for example, the random number, if I divide it by 100, it's the minimum number, which is this one right here. Okay, so now I have the range, which is distribute these 10,000 numbers. I get the remainder. So this is the equation for that, right? So this is a cool equation that I can get to generate a random number. So this will fall into 0 and 1, and I'm doing this for 10,000 times. 10,000 times I'm doing this, right? So if I do it, I'm sorry, this is 100,000 times. Yeah, I need only 10,000, so it's just like this, right? Okay, so so if I do this 10,000 times, and I'm going to map this into this histogram, right? So what does this means? This means if I get a number from 0 to 0.2 or the 0.1, I'm going to put it in this group right here. So this is 0 to 0.1, and how many times I'll get? Well, if I repeat this, for example, this is one of them, and of course this is 0.2, this is 0.2, so that will be on the other one, but everything in this one or less than this, so this guy, why? Because I'm dividing this by 100, so this will be 0.07, this will be 0.1, and so on if I divide this by 100, right? So, and this is 0, so this guy right here, right? And all that will fall into this piece right here, right? Okay, so that is your range actually. So this one says the average of the range. So the possible range, outcomes of possible range is 0 to 0.1 is one range here, right? And again, I might have some other numbers here which is falling in from 1 to 2, like for example, let's say I have 17 here, right? For example, if I divide this by 100, the remainder is 17, so the 17 divided by this 100, I get 1.7, right? I'm sorry, what I get 0.17, right? Right, so this is bigger than 0.1, so it's falling in some category here, right? So like that I can fill this part, so on I can fill the whole thing. So when you fill the whole thing by the 10,000 numbers in this range, at the end it will give me a graph look like this. So the top part of it, you can get the average value on it, right? So you can see all the pieces are very close together. So in that case, you can say average, this distribution is even. Why? I can draw one line which is meets all these top parts pretty close, right? So the average wise, I can say this is a pretty nicely evenly distributed when you're running this random number. I mean this equation 10,000 times, I get some values in this range, means I get some evenly distributed manner, right? So this is the idea of this whole lecture, how you distribute numbers in many different ways, right? Well, okay, so the next question is, why is it important? Why you want to do that? Well, the one reason is, well, if you have numbers that distribute randomly, and then if you want to calculate the average of if something occurred many times, and if you want to get just the close enough value for all the occurrences, well, then you have to distribute it and then see where is it falling into. And the other practical sense of this is, especially in computer graphics, is called, if you ever heard the Barnsley's fun. This is something I give for the students in my graphic class to generate. The Barnsley's fun is pretty interesting concept, so I will share that with you. This is the Barnsley's fun. This is what we call Barnsley's fun. Okay, and this is how what is generating. So in order to generate this one, actually what you do is, I will throw up 100,000 or more seeds, the dots. So if you have more dots, less dots, you will have something look like this. But if you have more dots like 200,000 or above, you will have nicely designed fern. So how do I get this? Well, if you want to get read about it, it's in the Wikipedia, right? And so what you do here is you get some equations, four of them, four equations here, and I would say, okay, if you generate 100 random numbers, let's say I'm generating 100 random numbers, okay, and out of 100 numbers, if my number, so I'm doing a random number 100 times, right, and if my number is falling into 1%, right, so that means falling into the range of 1. So that means if my number is 1, basically that's what it is. If my number is 1, I'm going to assign my xy values to this. So it will draw some dots if I generate my random number is 1. If my random number is from 2 to let's say 2 to 85, right, or 86 actually, yes, 86. If it is falling into this range, I'm going to use this equation. And if my number is from 86 to 92, I will use actually let's say now yeah, if it is in this range, I would use this equation. And then if it is the rest, if it's like 93 to 100, well, in that case I use this one, right? So if I use this equation, so that means evenly distributed, then whatever the number I get, 1% of the numbers I get, I'm just doing this, and 85% of the numbers I'm doing this, 7% of numbers I'm doing this, 7% of numbers I'm doing this, right? So that's what, maybe this is a little bit, I have to take care of the range properly. I'm just giving average thing. So this is what it is. If you do 100 times, if it is falling into 1, you do this equation. If it is falling into 2 to 85 or 86, so you're taking this equation. And if it is 86 to 93, you do this equation, and 93 to 100, you do this equation. So when you do these equations, and if you do that for 100,000 random generated numbers, you will get magic output, which is what you do here is actually you plotting the numbers. So that means I'm plotting x and y values. I'm just drawing dots. So if you draw dots with the seeds that the iterations I'm doing this, it will give you a pretty nice outcome, which is look like this, which is called the Barnsley's fern. So that is pretty neat way of doing things. You may and also we call this fractals, right? So these are things we call fractals. If you are a computer scientist and if you're interested in fractals, or if you're a mathematician, it will be pretty great things that you can learn. One interesting part on this is you notice this one give you the natural outcome, right? So it is a function that give you this look. So that makes sense how we made up, right? If you're looking at the sunflower, it is also having certain patterns. So you call those fractals. You can generate things like that. Okay. So that is a little extra, is just to explain what is a distribution and why is it important. So that was the distribution, that the one I was talking about is you throwing out 200,000 to whatever the number of iterations, and you map that according to an equation. So in this case it is just mapping the range as is. But if you map it to an equation like that also, you get a pretty neat outcome, right? Okay. Alright, so that is the idea of distribution. In this, the distribution I was just showing on the Barnsley's Bernie's, the furnace, it is about distribution of values in a percentage, like 1 and then 2 to 785 and so on. So you have the range, of course. Again, that range is not equal range. It will have a different range. In this case, we have equal ranges, right? So this is just a 0.1 on each of these, right? And we just generate some numbers and distribute evenly. Okay, so I hope you understand that part. Alright, so there are two ways that you can understand this. One is, of course, I don't know whether the reading a book itself helped you that much, and because you need a little bit insight in order to understand this concept. So that's why I try to put some examples and show you how you're really going to distribute things. Okay, so we'll look at another example. Hope that you will get the idea from that. Okay, right. So right, so the move on to the next. Here it is. It says, okay, so in this part, let's explain what I exactly explained in the first. I was discussing this part right here, which is 10,000 random numbers, and I'm just mapping that. So this is what it is. But how do I subdivide this? So in this case, how many intervals I'm making this, right? So here, one way of looking at it is, suppose we break the interval 0 to 1 in 5 intervals. So that is the range. So in that case, what is the range value is going to be? If the list contains 100 random numbers, so I'm going to break these 100 random numbers into the given interval, or the average sub intervals, as you divide the 100 by 5. So it is 20 at a time. So that's what the number intervals that you're going to get, right? So the number of intervals in this case. In my case, I have, how many intervals I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I have 10 intervals in this. This example, I have whatever the number, I'm just breaking into 10 intervals, right? So what is the range? So that's what it says. What is the average value? So I'm going to get, if I divide 0 to 5 in 5 intervals, I get 20 as the average sub-interval average. If I get 10 like this, so it will be like 100 divided by 10. So that is the average value it's going to be, right? Okay, so that is something that you have to keep in mind. So that's what it is. So it says number between 0 and 1, and how many sub-intervals that you can break it is your average. So usually the number n random numbers between 0 and 1 divided by the how many sub-intervals you want. This is what we call average. Okay, so you may see here, let me emphasize this with that concept, so you'll understand what I'm talking about. Let's say I have 10,000, right? So here I have 10,000 numbers, right? And yeah, oops, 10,000 numbers, and I want to have what is the average of the values if I break it into 10 intervals, right? Is I'm just dividing this by 10. So the average I usually get is nothing but 1,000 here, right? This to this cancel out, so I have 1,000. So that's why I have 1,000 range right here. So that is the maximum values or whatever the range that you get. So if it is evenly distributed, this concept holds. So that's why n divided by number of intervals I'm going to get will be giving you the average. So that's what it means. Okay, right. So this is what it means. Right. So yeah, I think it's clear enough. Okay, so that's one of the concepts they're describing in the book. Right. Okay, so then so this is the example of it. So it's n divided by this. Right, so now we come to another interesting point, the discrete distribution and continuous distribution. So what is this means, right? Well, what is the continuous distribution and what is discrete distribution? Well, mostly we are talking about only the discrete distribution. Now the continuous distribution is something very difficult to calculate actually. There's no probability or occurrences can happen if it is a continuous. Why? Well, first thing, let me talk about what is discrete and what is continuous, right? We talked about that earlier as well. So the best thing I can do here to explain that in a different way, let's get a digital clock, right? If it is showing something like this in your digital clock, next time it will show you something like this, right? So in this case it will jump from here to here, right? This is just numbers, so it's jumping. So this is actually discrete. This is a good way of explaining the discrete thing, right? Sorry, discrete, yes. Discrete, the what is the concept of discrete, can explain in this way, right? What about if you have analog things like this kind of a clock, which I have two hands, things like that. So in order for this guy to move from here to here, even its jump, right, it takes time, right? It is not instant like this one. It has to pass this point one way or the other. It has to pass this point one way or the other in order to reach here. So that means what? That is always continuous. There are it's regardless of the speed, it has to go across these points. So that means the number of ways that you can divide this is actually infinity. There's so many ways. I mean the interval or the range that you divide this distance is infinite, right? So you can actually divide this out 1 out of 10 or 1 out of 100. Still it's hold this because it's continuously moving. It is not going, there's no way that you can disappear here at this, disappear here and appear here. You have to pass this length. So that is why this one is always continuous, right? So it is continuous. But here there's no such a thing. In between it can be blank, but it will come up very quickly. So it's a discrete. In this case you have to pass each and every point here. In that case it is continuous. So that is the idea of continuous and discrete, right? Okay, so then what is this says? Well, this says pretty interesting factor here, saying the probability of occurrence of any value on the continuous distribution is 0. What does that means, right? What does this means? Well, the one thing you know, what is probability? The probability is total number of occurrences, right? Total number of occurrences, and how many times you get some value, right? So that is what this is the event, and this is what we call total events. Total events, you divide the events by total events, is we call probability, right? Okay, so what about this total events in the continuous function? So there are so many events, like for example, if my piece is going from here to here, right? So if this is going like this, I can divide these sub intervals as much as I want, right? So this sub intervals, if you take from here to here, is actually infinite. So you can divide this to any number, right, and divide the events from that. Right, what is infinite number? Divide any number by the infinity is also 0, right? Right, so this is actually what it means by this statement right here. Okay, so that means you cannot exactly say this is the total number of events is going to happen. So it can be anything. So because of that, the probability of that is infinite. Right, so because of that, you may have to get a range and then the interval. So that's why you just talk about discrete distribution instead of continuous distribution. Continuous distribution is very hard to calculate because of you don't know how many divisions is going to be happen. Right, so from now on, because of this reason, we're going to discuss discrete distribution in different ways. So that is what this lecture is all about. So I hope you understand up to this level. So if it is not, just go ahead and listen to this again. So if it is not, you can just always contact me and clarify your doubts, right? Okay, so the graph of the probability density function px equal 1 uniformly generated random numbers with the values from 0 to 1. So this is 0 and this is 1, and I'm just having the same kind of a thing that we were talking about earlier. There's a distribution of some numbers, right, and then the probability of that uniform random floating number between 0 and 1 falls in. So okay, so now I have a random number which falls into this range, which is 0.6 to 0.8, right? So we already talked about this earlier, right? So so what does this means? The integral of the function fx from equals 1 from, so that means here it is it says the average value here is 1. So what does this means actually? Alright, so what they're talking about here? Well, they're talking about they're saying that the probability of if you have a uniform random floating number distribution, so this is just a 1 for everything, right? So it's the average, and the probability of your the number whatever you pick by random falling into this range right here, so falling into this range right here is the saying is that is also equal to the integral of, so that means the integral means if you have a function, this is actually, what is this function? Y equals 1, right? So all the x you have 1 actually, so that is what this equation is. Or I can write it fx equals 1, so that is the line right here, right? So this is the equation for this line, right? And it says, okay, so if I want to calculate this range right here, that is nothing but you can say 0.6 to 0.8 and fx, so this is what it says, okay? Or I can calculate manually, obviously. This is 0.2 multiplied by the height is this, so that is the area. So the area also equals to 1 multiplied by 0.8 minus 0.6, so which is give you 0.2, right? Okay, so if I take this one as so this is from 0 to 1, so if it is 1, if it is 1 on the range, you get 0.2 times, I'm going to get that value. If it is 100 in that case, if it is 100 in that case, you get 2.0. So this means what? This means that 20% of the time I get this range. If I throw a dice or whatever it is, if I generate random numbers, those numbers will falling into this group right here 20% of time. So that's what they're talking here, and then try to explain. Has nothing to do with anything else. It's just discussing how you analyze this and what is this means if you have some things like this. So this is what something we call the probability density function for the distribution, right? That is what the term that they are trying to explain here. Okay, right. So let's move to the next kind, and we're going to look at bunch of distribution types. So this is probability function returns the probability of the the probability of occurrences in a particular argument. Of course, this is the argument is right. What is the range of numbers I get? What is the probability of having some numbers in the range of 0.8 to 0.6? That is your particular argument, and then you can calculate it. And also, if you want to calculate the probability for continuous function, obviously you have to set up a range. So if you have the range, so that means the total events will be limited. So in that case, you will have something to divide your outcome. So that means that will give you the probability of a continuous function. So it always has to have a range in that case. Okay, so that's what they're talking about here. Right, so there is another example of a discrete distribution, right? So in here, in the generation of random numbers to represent, so you throw a dice. So that is a nice way of picking a random number, right? So you just throw something, and it will give you a random number 6 or whatever the dice gives you. So those are values that you can have 1, 2, 3, 4, 5, and 6. So you definitely know the numbers you get is in this range, 1 to 6. So since it is a range of this, then it's always like that. So you call this a discrete model, right? So you can always get discrete value. Okay, so then it says, okay, so I have these values, so I want to see what is the probability of getting one value here, right? So what can you do? I can divide this to what? I can divide these to 6 submodels, right? And you can consider that as your intervals, or the total possibilities that you have here. The total possibilities you have here is nothing but 6, right? Yeah. And having this one of these numbers out of 6, right? For example, right here they're talking about something something you get argument 2, right here. And if I do something and then trying to get argument 2 as my result, so what is the probability I'm going to have that? So yeah, so total number of probability I have in each iteration of throwing this is 6, and out of 6 the probabilities I have only 2 ones. So in that case, this is 1 over 6 is the probability of having this number or any other number, and you having something like this. Okay, right. So that is actually the probability explaining here. And also they are talking about probability density function with an argument of 2. Well, it is the same case because I have the total event and how many times 2 might be coming to play. Right, so this is actually, I'm ending here with the continuous distribution. If you need something on that, well, and then we're going to talk about all the discrete distribution, right? So when you're talking about discrete distribution, so you set up some ranges and see how your values are going to distribute evenly on that. So that is what the next section talking about. To generate random numbers in a discrete distribution with equal probabilities for each n events, generate a uniform random integer, right, for sequence of n integers, where each integer corresponded to an event. Okay, so let's look at this. I don't want to explain this in English. It's better we pick up some example and visualize that so you can have some idea without trying to throw some vocabulary in it. Okay. On this example, what they're doing is they set up a little rat. So we have a rat in a cage, and so yeah, he's putting in a little cage like this, and each time you let him go out, and then there are some food lever, so you can go and raise this little lever thing here and get food, or there's a little one here for the water, and he doesn't want to do anything else, so he just walk around. So those are three things he can do. Either he can pick water, he can pick food, and then he can walk around. So, and then you do this iteration so many times. I'd say I'm doing 100 times this iteration. So there's a little rat here, and what I'm doing is I'm letting him go out 100 times. So when he go out of 100 times, he will do 15 times he will go and pick food. So I'm saying this one is go out and pick the food 15 times. And then other 20 times he will do this, go and pick the water. Other times he just roaming around, alright, not doing anything. Okay? So out of 100 tries, 15 he does this, 20 he does this. How much? He doesn't do anything. Well, you add these two and subtract by 100. So in this case, this is 35, right? So the 65% of the time he doesn't do anything. Okay, 65%. So what is this percent comes? Well, if you do something 100 times, how many times you do each, right? So in this case, if I get 100 times, this guy is doing 15 times food is 15. So if I want to divide the rest into these numbers, so in this scale value right here, so this is the 100th time I do this, and I'm mapping this pretty nicely here. So the 15 times I do this, and that means 15 to 35 I do something else, right? So what is the difference between these two? 15 and 35 is 20, right? So probably I get it perfectly right. And then between 1 and 35 is 65. So that's why if you have 100 times, if you have 65 times, if you do this, that means the 65% he doesn't do anything. 20% he did water, and the 15% he did food. So this is what it explains here, right? And so this is how you're really going to map this. This is the same thing on the Barnsley Fund. If you have 200,000 and you just map it to 0 to 1 and pick how many times this range falls in, how many times this range falls in, and then you map a graph using the equation for those kind of occurrences. So that's how you get the Barnsley's Fund as well. Okay, right. So this is about distribution, how you represent the distribution on a scale factor. Right. So I'm doing something 100 times, and then I figure out, okay, this many times this occurs, this many times this occurs, and the rest is this. So in that case, it is a percentage because I took it for out of 100 tries, right? So that's what it is. Right. So always it is better that you will have something out of 100. So let us give you a clear idea what it is, right? So here is how you represent that in the equation, right? So if a random number is less than 15, so you throw something and you generate the random number, right? So obviously you need the equation here. So what is the equation? Again, so the equation for this is actually rand, right? So this is rand. That's the random number, and let's generate some number here and mod that by 100. So the modulate by 100, That means I'm taking only the remainder, right? And yeah, so if I have this one and it will fall into this, if I want to get it with 0.15, so like it says there, divide this by 100. So this is what actually random number means. So this means this actually, right? And if I divide it by 100, if I get less than 15, right? If I get less than 15, well, I'll do this guy right here. And if I get 35 to 75, so that is the range, I get this one by doing this. And then other times that you don't do anything means you can say else, right? So you can say else. So if this range is this range and all the rest of it, so that's what it means, right? Okay, so this is how you actually writing that in a code, especially if you're writing algorithms and stuff for the computer science people. Okay, I don't think the other people should be interested on that anyway. All right, so that is one thing. So then you come to generate random numbers in a discrete distribution. Probability. So what does this mean? Okay, so you add all the possibilities together, so at the end, right? Or you can actually generate each uniform floating point numbers in a given range from 0 to 1. So what is these two different brackets here? So this one it says exactly 0, and then this one says okay, a little before 1, right? So what this means is you give a range from exactly 0 to closer to 1. So that means I'm not taking my 1 as the count. It's not like this. So if I take like this, so that means I'm going exactly 0 to 1. So in this case, this is 0. So this is exactly 0 to little bit before 1. So it is 9, 9, 9, 9, 9, and so on. So many bunch of 9s you can put in there, right? Yeah, so what I mean is, yes, so this, you don't see that there. So this is exactly 0 to 0.9999 and 9, so on. So many 9s in there. Okay, so that is the range that you're talking about, 0 to 1. Okay, so that's what it means. And then okay, so if it is less than p probability, in this case, what I do, well, what I'm talking about here is probability of distribution, right? Let's check. All right, so yeah, so this is already done talking about it. So this one is generating random numbers in discrete distribution in probabilities. So this is actually, the probability means a little square. Each of these squares are the probability of that range. So this is the probability of this range, and I have a few more. So that is what they're talking about. If I want to add or represent that in one way that you can do is add all together, and it should be 1, right? And if you really want to get uniform random distribution, if the random number is less than p1, then return e1, and so on. So this is the event, right? And the event divided by the total possibilities will be your probability, right? So that is, we already learned that. I was talking about just a minute ago, right? So anyway, what this means is you can get the probabilities on each step like this. If the random number is less than p1, then you call it e1 as your event, and the else, if it is p plus 2, it is less than that, means it's the range of p1 to p2 kind of thing, and if it is on that one, we just call it e2, and so on. So this is just a generate distribution. Okay, so there's nothing much in it for me to explain. Okay, so there's something called a normal distribution. So this is what the normal distribution means. So let's talk about this for a minute. Okay, so in this case, what you do is, I want to distribute some numbers in the range of, well, you call it x here, in the range from -3 to +3. So that is your x range. And so if you have something like that in my x range, and I throw that to my equation and see what is I get as my y, right? So in this case, you have two more equations here. One is called for the mean, and then the other is the standard deviation. I already talked about what is mean and standard deviation on the previous lecture, right? So if you forget it, go and check. What is mean is actually if you have some values like this, like this, like this. So I have 4, so I add all 4 and divide by this. This is what mean of value, right? So the standard deviation is you just take this value, which is whatever I get here as my mean, and what I'm doing is I will get a square root of the mean. So this is m, so I get the square of value minus mean plus the other value minus mean square plus, and so on. You just add all together like that, and then 7 minus mean squared plus 10 minus mean squared. So and you divide by 4. So this is what actually the square root of standard deviation means. Okay, so this is what the standard deviation. So in this equation I have pi, which is already pi is the value of 3.1459 something, and then I have the standard deviation in two places here, right? And then I have x value, and then I have mean, which is the mean like this, right? And then x is 1, which is I'm going from -3 to +3. And when you calculate this value for the x value there, you get, when you using this equation, you get pretty nice y values like this. Okay, so for example, if my x is 0, right, if I throw that here, 2 pi, and then this guy multiplied by e to the power positive mu squared divided by 2 this. So this is what your y value is going to be when right here. So this is actually supposed to be give you 4 in this case, and the other values I can map. If I have 1, obviously this one will be 1. In that case you will have this, and then this, and this. Yeah, so this is when you're having 1, so it will give you exactly this one. If it is -1, it will give you this value. So like that, so you can distribute this pretty nicely. And one thing you may notice, the highest number of probabilities that you can get, maybe 96% of them here falls into, I think it's 96, yeah, that's what the book says. If you want to, this is something they're explaining with the values in there. As I remember, that says 96 of the time for this particular example, right? I'm sorry, yeah, so the 98 times, we think that, no, I mean 68 times. So 68, in the book it says, yeah, 68 times you will get that range, right? And also, so in this range is, out of all the 68 times you get this range, right? Okay, so and then if I want to get into this range right here to here, all this it says 95% of the time it will be distributed to that range, right? So yeah, and from here to here, the total range from plus or minus from here to here, it says it is not 100%, it says 99.7% of the values will range from here to here. So it's not always 100, it says that when they explain this. But what is interesting in here for you is if you want to have the equal bell-shaped distribution, this is the equation you should apply for your random numbers, or whatever the number you just apply as your x, right? Okay, so so whenever you have that range of x values plus or minus, this is what you get as your y value. So this is what we call a normal distribution. So this is the equation for the normal distribution, and as I show you, when you're having x values, this is what it's going to create. Okay, and yes, you're mapping these x values right here, and it will generate the y equation. So this is actually the distribution that you get if you're using a normal distribution function. Okay, so that is a normal distribution function, and then this is a Box-Muller method for normal distribution. So that means it's also have the mean and min, I mean the mean and standard deviation, but in this case I'm using some sine and cosine values, right? And I have the random values in my B, so on. So when you're doing this kind of a Box-Muller method to distribute values, you will have this kind of equation, right? So what you have to know here is what are these each of the point means. So here it says, okay, the sign is a sign, we know already in math, this part we know, and yeah, this one is the mean, that is also we know how to calculate now, and yeah, so you have those two. And then what is b here? So the b is nothing but this value right here. So what is this? The natural log of the random number I generated, and it can be a minus values in that case because I'm multiplying by the -2, so it will be positive, and you get the square root of that multiplied by the standard deviation. So this is Box-Muller. He's explaining this kind of this type of distribution, right? So what you should know here is what are these terms means. Okay, so this is also from 0 to just little than 2 pi. Okay, so that's what it means. Exactly not touching 2 pi, it is just before that, right? Okay, so when you're using the Box-Muller method to do the distribution, you have to know these equations right here. This is the mean, the standard deviation, mean, and these values, and then you can generate the Box-Muller method of distribution, right? Okay, so that is that, and then let me talk about exponential distribution. So what you're learning here is 3 things, right? First is, let me catch up real quick if you're losing the track. Discrete distribution, we talk about what is discrete means, and we talk about this example. And then we're going to do the normal distribution, which is you using an equation like this and then generate all the map things like that. So now you know that part. And then also the Box-Muller, you have to have an equation like this, and then you generate the values that you want, right? In this case, obviously using a random number, uniform random number by a. So this is a is the random number, and you distribute this. And the other one is called exponential distribution. So this will be the last one I'm just going to introduce. Well, only thing that I'm expecting you to know in this one is there are different kind of distributions. That's the one thing I like you to know. The other is how you distribute numbers, the huge numbers, into a given range. like the example I just worked on at the beginning, right? 10,000 numbers, and then I've distributed to 0 and 1. How are you really going to do that? That is the one part. Okay, so this is exponential method, which is using by we use this one for the population growth and all that, right? So how do you map this or distribute the values I get out of this, right? So when you're doing this, obviously you have to calculate all this, right? Okay, and then you can come up with the value. So the rand part is uniformly you just generate numbers from 0 to little less than 1, right? And then that is your random value. So I get the logarithm of that and divide by r. That is just taking care of this equation. And then I say the r is always less than 0 and the t is greater than 1 and 0. And when you're having this, r is the rate actually, right? And it says r is with r is always greater than 0 and the t is less than 0. In that case, if you have this equation, you calculate the linear random function over r, right? So this is I mean the natural log random function over r, right? And this is what how you calculate the random number is you just give the range for the random number 0 to 1.0, right? Or obviously you can do it this means actually you have a number and then you mod it by 100 exactly. So it will be never going to be 100, it's going to be 99, and then the last part is will be 0 to 99 is the range. What I mean is if I really want to generate my random numbers in this range right here, right, this range right here, I just simply say rand mod 100. Okay, so this means I'm never going to get 100 here, so only maximum number I get is 99, so it is not 100, but the 0 obviously we're going to get. So that's why this is a square on this side and the circle, half circle on this side, or the parentheses on that side, right? So that's the range they're talking about. Okay, so this is another way of doing the distribution. So this one is called exponential distribution. So okay, so as a summary on this lecture, I'd like you to know these things. What I want you to know, well, what is this means by 10,000 random numbers distribute into 0 and 1? What is this means? So that's one thing. I just go through example of this. If you don't understand, go through that again. And yes, what is this means, right? So this part right here, I was explaining that as well. And what is discrete and what is continuous? Give me some examples of it. And then obviously yeah, go through this example and also know what is discrete distribution, right? This is a very good example. I would test you on this, and then yeah, there's nothing much in there. So, and then what is normal distribution? If you want to, if I give some values, can you calculate it out of this? And yeah, and then what is Box-Muller distribution? If I give some value, can you calculate on this? And then exponential values. So what does this mean? Well, it's already straightforward, giving you the equation. In that case, there's nothing much that I can test you for. So this is a probabilistic density function. If you're using these values right here, right? So this is what the graphics look like. Okay, so this I call a lecture, and then we're looking into the random walk next time.